Okay, picture this. Your team has just launched a brand new system, and on paper, it is an absolute masterpiece. It's clean, it's well-tested, it's supposed to be incredibly fast. But then it hits the real world, and it's slow. Mysteriously slow, and nobody can figure out why. Today, we're going to dive into a real-life engineering detective story about a performance bug that, well, wasn't a bug at all. So the story kicks off with a team that built this super high-performance API gateway. Its whole job was to handle authentication and do it in a flash. They push it to production, feeling great, but almost right away, the alarms start going off. The very first requests after every single deployment are sluggish, just slow. And that's a terrible first impression for any user. Now, this is where it gets really interesting. Just look at that difference. In their controlled lab tests, the benchmarks, the API was responding in a blazing fast 8 milliseconds. Awesome, right? But in the real world, in production, it was a painful 40 milliseconds. That is a 5-fold slowdown, and it happened like clockwork every time a new container spun up. So this is the million-dollar question that was just haunting the engineering team. The performance wasn't just a little bit worse, it had completely vanished. It was gone. And this kicks off a major investigation to hunt down the ghost in their machine. All right, so the hunt begins. The team starts where anyone would. They look at all the usual suspects, the common things that cause slowdowns in production. And they did everything by the book. They checked container startup times. Nope, the container was fully up and running. They looked at the database connection pool. Was it healthy? Yep, totally responsive. They analyzed network latency. Nothing weird there, completely normal. All the obvious answers turned out to be dead ends. And this is where the mystery really, really deepens. They fire up the code profiler, which is supposed to be the ultimate tool for finding these bottlenecks. But it found nothing. Not a thing. No single function was slow. Instead, the entire execution was just dragging its feet. The slowness was spread out like this thin fog, It was everywhere and nowhere all at once. So after ruling out their own code and all their infrastructure, the team had to look even deeper. They had to look into the very heart of the Node.js runtime itself, the V8 JavaScript engine. And what they found was that the problem wasn't a bug. It was a feature. It was a fundamental piece of how V8 is designed to work. The culprit has a name, and it's called adaptive compilation. You see, V8 doesn't just run your code at one speed. It has this really clever strategy. It starts off by running your code kind of slowly, using something called an interpreter. And while it's doing that, it's watching. It's learning how the code behaves. Only after it's gathered enough data does it go back and compile the really important parts into super fast machine code. So a good way to think about V8 is that it has two different engines, or maybe two different gears. First, there's Ignition, the interpreter. Its main job is to get your code running immediately, super fast startup. But the actual execution, it's pretty slow. And then there's TurboFan. This is the optimizing compiler. It takes a little while to warm up, but once it kicks in, your code runs at absolutely incredible speeds. So here's kind of how that whole pipeline works. When your function runs for the very first time, Ignition is the one executing it. And as it's running, it's collecting feedback. It's asking, okay, what types of data are being used here? Which if statements are being taken most often? Once a function gets called a lot and is identified as a hot, V8 hands it over to TurboFan, which uses all that feedback to create this new, highly optimized version. And the difference here is just staggering. We are not talking about a small 10 or 20% improvement. Code that's been optimized by TurboFan can run anywhere from 10 to 100 times faster than when it was just being interpreted by Ignition. This is that peak performance the team was seeing in their benchmarks, and they couldn't figure out why they weren't seeing it in production. But, and this is a huge but, there's a catch. TurboFan's optimizations are basically just educated guesses. It's making an assumption that your code will keep behaving the way it did during that initial learning phase. If that assumption turns out to be wrong, like say a function suddenly gets a string when it was always getting a number before, V8 panics. It throws away all that fast code in an event we call deoptimization, and it falls all the way back to the slow Ignition interpreter to start over. Okay, so now we get the mechanism. This isn't some weird bug. It's a deliberate design choice by the V8 team. And it creates this fundamental trade-off that, honestly, every developer working with this stuff needs to understand. And this slide really lays out the conflict perfectly. On one hand, you want your code to start running instantly, right? That's what Ignition gives you. But on the other hand, You want it to run as fast as humanly possible, and that's TurboFan's job. The thing is, you can't have both at the exact same moment. There is always a warm-up period to get from one to the other. This is probably the single most important insight from this entire investigation. The team's code was already fast. Trying to tweak a function here or shave a millisecond there would have done absolutely nothing. The problem wasn't the code. It was the entire system's design and how it was interacting with the V8 engine. You have to design your system with this warm-up penalty in mind. So how did they fix it? This is the best part. They didn't even touch the application code. Instead, they completely changed their deployment strategy to work with V8's behavior, not fight against it. The right way to think about this is to match your system to V8's strengths. So if you're building short-lived processes, like serverless functions that are constantly spinning up and down, you're pretty much always going to be living in Ignition's world. Your focus has to be on fast startup. But if you have long-lived servers, you can afford to pay that warm-up cost one time and then just enjoy that peak TurboFan performance for millions and millions of requests. So the team's actual solution had three key parts. First, they stopped constantly killing and restarting their instances. They moved to a much more stable pool of long-lived servers that could actually stay warm. Second, they set up something called connection draining, which gracefully transitions users off old instances instead of just abruptly killing them. And third, and this is super clever, they added monitoring to actually see the V8 optimization status, so they could track the balance between slow interpreted code and fast optimized code across their whole fleet. This whole story, it kind of forces us to ask a bigger and maybe more uncomfortable question about how we measure performance in the first place. You know that teams' benchmarks weren't wrong, not technically. They showed the system's absolute peak potential after it had warmed up. But production revealed the cold, hard truth of their deployment pattern. They were stuck in a constant, never-ending state of warming up. Their benchmarks showed a best-case scenario that their real-world operations never, ever let them reach. And look, this is not some obscure, isolated problem that only affects one team. It affects a huge chunk of modern software architecture. If you're using serverless or containerized microservices or systems that autoscale, or if you're deploying multiple times a day, you are paying this warm-up tax, whether you realize it or not. So I'll just leave you with this question to think about for your own projects. Are you measuring the performance that actually matters? Is your system genuinely fast under the chaotic, unpredictable conditions of the real world of production? Or is it just fast in the sterile, perfect world of a benchmark? The answer might just surprise you.